All right, now we're going to introduce Unit 4, the last unit in the class. So in Unit 4, we've dealt now with motion of molecules, we've dealt with electron energy, and now we're going to tie these two things together to generate chemical bonds. And basically what we're going to do is, we already remember from Unit 2, we addressed this thing we called a Morse potential, which described the vibrational motion. We used it to describe the vibrational motion of a diatomic molecule. We had a homework on BRO, and we addressed various other molecules as well, in the context of what's called an anharmonic oscillation, meaning that it wasn't just a parabolic potential, and specifically it has a bond strength. So the critical thing we want to address now is, where on earth does this thing come from? So what is the actual source of this Morse potential? And to do that, we have to return to our favorite proton, which is Pauli the proton. So there's Pauli, and Pauli is going to be the proton A, because this Morse potential over here is a function of the distance, the internuclear distance, RAB in angstroms. And so Pauli will be proton A here, but we need a B. So over here is going to be proton B, or nucleus B, and we're going to call that OPI for reasons that should become evident in a little bit. OPI is J. Robert Oppenheimer, and that is going to be proton or nucleus B. Formally, we could give it a charge plus Z. For most of this discussion, it's going to have a charge of plus 1. So those are our two nuclei now, and they're some distance apart. So that's our RAB, and that's actually the Z coordinate in this coordinate system. So one thing that introducing two nuclei does that we didn't have before is, now that there's an intrinsic Z direction to this problem, and that's the vector that points between proton A and proton B. And so that Z component will become important later on when we start to describe various electronic states for this system. Now we've got a little problem here, which is that these two nuclei, Pauli and OPI, they don't like each other very much. And so if we look at their interaction, there's going to be a part of the potential energy term here that we call the nuclear repulsion term. And we'll call that VAB, and it'll have various terms associated with it. But it's equal to 2 Rydbergs times the charges of those protons, which usually are going to be 1, for this example at least, then divided by the distance between them. So like all electrostatic terms, it gets stronger and stronger and stronger as they get closer and closer and closer together. But in this case, because the charges are both positive, the energy is positive, which means it's repulsive. So the two electrons, the two nuclei, I'm sorry, really hate each other. And this term here, the nuclear repulsion term, is a central part of the problem. Now another part of the problem is that we've got an electron, right? If we just had a nuclear repulsion term, this would be pretty boring. If we have 2 protons and we try to bounce them off of each other, they're going to get so close to each other, they'll push each other away, and off they go. But now we've got an electron, this tiny red dot here, with a negative charge. That, of course, is Clarissa. So Clarissa comes into the show here, and Clarissa is going to be some distance away from Pauli there. That's RA1 in our jargon. And Clarissa likes that, right? Because Pauli is a positive charge, Clarissa is a negative charge, and now that electrostatic interaction is binding. That's just like the hydrogen atom. But in addition to that, there's this extra term, because Clarissa is also a distance RB1 from OPI, and Clarissa likes that too. So now there are 2 nuclei to attract the electron, and that can lead to a net negative energy. And of course the trick is to see whether there are situations where the overall negative energy from Clarissa interacting with both Pauli and OPI can offset that positive nuclear repulsion term over there on the right. And if we can find such a situation, we're going to have a happy balance and actually make a chemical bond. So now we can also quantify the interactions of, oh yeah, I should point out that those distances, of course, are all vectors, and also, if we're really setting up the problem, the way it gets set up is at the center of mass of the system. which in this case is right between the two protons if they're both single protons, and we define the distance vectors from that center of mass to A, B, and the electron, and then all of these RABs, RA1s, RB1s, etc. are vectors. They're the vector difference of the different coordinates of all of the molecules, and that gets rather complicated. Actually, it turns out the math for this problem, if we have a single electron and two protons that are fixed in space, if we force them to stand in a certain spot, that can be solved. But it's very, very hard math, and we're not going to go there. But there are actually solutions to that problem. Once you let the nuclei wander around, then the solution, an analytical solution, is no longer possible. It's what we call a three-body problem, and it can't be solved. But so we've got these the distances from the nuclei to Clarissa, and those lead to bonding interactions, so negative energies. And those are simply -2 Rydbergs times, again, the charge of the individual nuclei, which is usually going to be 1 in this example, divided by the distance between Clarissa and the nucleus. And the difference between the electron nuclear terms and the nuclear terms is pretty much one of speed and wavelength. So we already know that if we're going to solve even the interaction of Clarissa with a single nucleus, that we wind up with a wave function. We always wind up with wave functions, and Clarissa is going to be quite delocalized, right? The wave function has a lot of probability density all over the place within a Bohr radius or so of that nucleus, and that's kind of the we can't just specify the interaction at one point in space and close up shop and say that we're done. And that's what makes the problem hard. So what we're going to do here is exactly what I alluded to earlier. We're going to force the nuclei to stay put. And specifically, we're going to invoke this thing called the Born-Oppenheimer approximation. And one way to put it is electrons are fast and smart, like Clarissa, and nuclei, like Pauli and Oppi, are slow and dumb. And basically, they're going to take a long time to move around. Their characteristic motion timescales are just the frequencies, right? Of, for instance, an HH vibration has a time scale. It's got a frequency of order 4,000 wave numbers, and that translates into some megahertz frequencies. And so that's not that fast compared to the time scale of electronic motion, which is orders and orders of magnitude, more than 3 orders of magnitude higher. So electrons move around fast, and the idea is that we're going to force the nuclei to stand at a fixed distance and let Clarissa figure out everything that Clarissa wants to figure out about energy and find a nice solution to the Schrödinger equation for fixed internuclear distance. And that means that this term here, the nuclear repulsion term, is basically a constant. At any given point in time, it's just a number. And so we're going to solve the electronic problem, and then we can take this positive number that's part of the interaction energy and just kind of add it back in. It's kind of this passive-aggressive, the two nuclei hate each other business, but they're not really doing anything about it. We're just letting Clarissa figure everything out, and then once Clarissa has taken enough time to find out what would be a good energy, basically, then we turn around and we ask Pauli and Oppi, what do you feel about this? And they typically answer, I don't feel very good about this, and they tell us exactly how bad they feel about it in terms of this plus 2RH times divided by the distance between them for charges of 1. So we'll break it down into first solve the electronic energy, then add back in this nuclear repulsion and pretend that it's exactly just a number. It's purely classical physics compared with the very high frequency, low mass motion of the electron. And remember, the smaller the mass, the more sort of quantum mechanic-y things are, and the electron is 2,000 times less massive than the nuclei, and so it's got an enormous leg up on being a quantum object And that's basically why this separation actually works. All right, so here's how we do this. We're going to set up a coordinate system. The nuclear distance RAB is our x variable. The energy in Rydbergs of hydrogen is going to be our y. And I got -1 and -4 here. Those are important. And there's, of course, a 0. And the x distance we're going to do in terms of Bohr radii. So that's a naught there. And I'm going to tick off 1 Bohr radius. So we have an electronic potential energy term here, VE we're going to call it. And again, this is -2 Rydbergs times the two attractive terms, the nuclear charge of Pauli, Za divided by Ra1, and then the nuclear charge of Api divided by the distance Rb1. And both those Za and Zb in almost all the cases we're going to be thinking about is just 1. We're going to be dealing with 2 protons here to start things off. So that's our electronic potential energy term. Nothing about the nucleus being said yet other than where it is, okay? So the nucleus, the nuclear term, we're not going to worry about yet. We just want to know what happens when I have this potential here. And we're going to start out way on the right-hand edge. And way on the right-hand edge, I can lay down my 2 nuclei and then draw the potential energy. So let's do that here. There's A and B and a dashed line between them. And then the potentials are going to look like this. And that's actually a big deal here. So remember when I drew that 1 over r potential long ago, and I said really r only is positive, and but I'm going to draw the negative side just so you can think of this sort of funnel that attracts the electron, because the potential, we're going to vary the angles theta and phi, and the potential will be spherically symmetrical about that. Well, now that back side of the interaction really kind of matters, because there's a second nucleus here. And so we really do have these 2 sort of holes in the potential energy landscape. They're 2 negatively pointing singularities. They go down to negative infinity. And with a multiple nuclei in big molecules, the potential space is filled with these little pinpricks of potentials going down to negative infinity, which really makes the problem kind of hard to solve, but it can be dealt with. So here at a large internuclear distance, those sort of 1 over r potentials that are shown in blue there, they look perfectly unperturbed. And the potential pretty much comes right back up to 0 in the midpoint between A and B. And in that circumstance, I can draw electronic energy levels at -1 Rydberg, -1/4 Rydberg, -1/9 of a Rydberg, just like hydrogen. And so pretty much when I drop Clarissa into this system, the low energy answer is going to be pick a well. Basically out of luck, we can put the electron next to Clarissa, or next to Pauli, or next to Api, and either way we're going to get a negative energy. We're going to get 1 hydrogen, neutral hydrogen atom, and then 1 proton, one cation, 1 positively charged proton that's very far away. The proton won't know anything better about it, and then way far away is going to be a neutrally charged neutral molecule of hydrogen, and so the proton will have almost no interaction with that anyway. So we know the answer to this. That energy is going to be -1 Rydberg, and I'm going to have a little wave function there. It's just going to be minus z squared, which is -1 times Rydberg over 1 over n squared for n equal 1, 2, 3, 4, 5, etc. That's unit 3. That's the hydrogen-like system, and I've got my energy there for infinite separation. Now, we can turn our attention to really close to actually the first thing I'm going to do is I'm going to put that there at -1 Rydberg, right, for z equals 1. Now I'm going to turn my attention to way over at r equals basically 0. So when RAB gets really small, now our 2 protons are extremely close together. And now when I go to draw in blue the potential energy, I can't even tell the difference between those 2 positive charges. So it looks like a +2 charge. Let's look at this. Now let's draw a little bit of x and y. And now I have a deeper potential. It's twice as deep because I have 2 charges really, really close to each other. And from the point of view of Clarissa, this thing looks like a helium nucleus. It's just a +2 charge. So now my energy levels go -4 because it's z squared, right? 1 + 1 squared minus 4 Rydbergs, minus 1 Rydberg, and minus 4 9/4 of a 4/9, excuse me, of a Rydberg for the n equals 3 state. And so now I have a new set of energy levels, but the lowest energy one, which is the one we care about at the moment, is minus 4 Rydbergs. And there is a wave function. There's our energy levels again. And also the characteristic distance there, if you remember from the 1s solution, it's like a naught divided by z. And so in this case, that characteristic distance is going to be about a half a Bohr radius. So the electron, the closest the electron can get in a sort of a characteristic sense to this pair of nuclei is about half a Bohr radius. And it doesn't, the point is once we get much closer together than about half a Bohr radius, it really isn't going to notice much about whether those charges are exactly on top of each other or just really close to each other. It doesn't really care. It samples the system exactly the same. And so that means the energy is going to get to minus 4 Rydbergs somewhere around half a Bohr radius or a little bit closer, and it's never going to get any better than that. That's the best we can do, is make a helium nucleus a +2 charge, and that's it. So there's our minus 4 Rydberg case.